remove first the kit. Okay. So I have to finish. Oh no, wait. Exams. Okay. We say that you have this first homework by Professor Monti. You will get 2 more from me. I confirm that you can also give the final exam through an oral examination. And starting from this year, you will also be able to give your final exam with the project. And I will discuss with you this project at the end of the course, more or less, so like 2 weeks before the end of the course. And this project will be like either I will let you free to design your favorite remote sensing system, and everything will be okay as long as it is correct. And typically these projects are presented in the form of a Word document or a PowerPoint presentation. I want to see equations, I want to see graphs, I want to see figures, I want to see a motivation. And as an alternative, I'm also planning to prepare for you some data. And so your project can be to do the data processing. So for example, I can give you radar data from a forest, and you will be tasked with estimating forest height, for example, or something of this kind. So let's say you will have more ways to take the final examination, but we will discuss this better in the future. For the moment, so if you want to be sure about what you want to do, you may stick to the old plan, which is homework/oral examination. Now, for today, we've been talking. Okay. So we talked about. Yeah.
Which is the difference in the exam if you do the homeworks or if you do the project? If you do the project, you don't have to do the oral examination. If you do the homeworks.
Well, typically, if you are very rushed, then passing the exams with these homeworks is by far the best option, because you can do the first one now, and then the second one, and the third one, and more or less right after Christmas you're set. If you want to give a project, this typically requires some more time and more thinking on your side. So let's say if you have to graduate in right after Christmas, then I suggest you to give homework. If you have more time, then the project can be nice and nice opportunity. Okay. So if you want to be sure to pass this exam right after Christmas, doing these homeworks is by far the best option. So I think we were here. Okay. And so we saw this is the equation for spherical waves. So spherical waves do emit from a point source. So the problems we are analyzing are linear. So if you have more than one point source, let's say 2 antennas excited with different signals, then you have 2 spherical waves that are propagating from the position of these 2 antennas. So again, this is amplitude. This is your signal, which is delayed according to the particular position that you are considering, and this is decimal signal. In the case of an extended source, well, an extended source basically, you see, the only difference is that we are substituting this delta with a continuous, with the signal. So let's say with the four-dimensional signal. So this says that for each point in this particular region of space, you have a time signal. So S of R and T. Okay, this is something that you can see simply as the collection of an infinite number of point-like sources. So what you do basically is that you can compute the field simply by integrating the expression of the field from any of these individual points over the volume of your source. Okay, this is easy. Easy for everyone. Good. Okay. Then I have to talk to you briefly about the Fourier transform of the wave. I think this is something that you really know very well. So basically, we want to pass from time to frequency. So the expression of our field in the Fourier domain is nothing else than a Fourier transform. So basically, we just take the Fourier transform with respect to time, and we end up with the field in frequency. And of course, what is interesting, as always, is that the expression of your field in time can always be thought as the integral of monochromatic waves. So this is a wave at a certain frequency, at a single fixed frequency, and this is its amplitude. So basically, this representation allows you to think of your field, which can be as complex as you like, as a collection of monochromatic waves, each with a different amplitude. So as simple as that. Of course, this is very convenient for us because we will have to. This building is really noisy. It's terrible and hot. Okay. So we will deal a lot with delays. You saw the principle. Now we just transmit a signal, so we receive the same signal with some delay. So we will deal a lot with expression of this kind. And so clearly, if you want to treat your field in the Fourier domain, all you have to do is to add this phase term. Is everybody fine with that? No? Okay. Sorry, these two first lectures are, let's say, meant to gain confidence in each other. So I am going slow and doing things that may be easy for you, but in case they don't, you will be stuck. So I'm just trying to understand what is the right pace. So for example, this is the expression of the plane waves in the Fourier domain. So where this delay just becomes a phase term, and exactly the same for the spherical waves. And this is it, I would say. Also very important to remember is that you can also transform Maxwell's equation in the frequency domain. And so basically the one difference is that the time derivative becomes much more easier to treat because a time derivative corresponds to multiplying the field by j 2 pi times f. So it's easy. And then you can again form the wave equation with the same procedure as in the time domain, and you end up with the famous Helmholtz equation, which describes a field in the frequency domain. So our spherical waves in the frequency domain are very simply expressed in this way. So instead of the delay, you have a phase, and of course in the case of an extended source, you have the integral of this field. And so basically you are integrating also all these phases. I just put a couple of slides on lossy media because it is always nice to remember what is happening, and because this is very easily understood starting from the Helmholtz equation. So with the lossy media, the assumption that we do, that we retain is again that the net charge is zero, so we are not considering any further charge in space. And but differently from the case of the free space, we do allow these charges to move in the presence of an electric field. So basically, the difference is that we also allow for this term, so we take the conductivity in the picture. No? Okay? And what we end up with is this expression. So basically you have here, ha fatto bene. Sì, sì, sì. Prego, prego, grazie. Yes, it's much better. So basically you have the same formalism as the Helmholtz equation, with the difference that this k square is complex. So it doesn't just depend on the permittivity and permeability, but also on conductivity. And you see that you have a J here. So this is a complex term, but formally this is exactly the same as the Helmholtz equation. So you can solve it in the same way. And assuming a plane wave, you end up again with a plane wave. So in this case, we have a plane wave that is just propagating along z. So z is the direction of propagation. You have exactly the same expression as in the free space, but this KC is now complex. So you can split it in its real and imaginary part. The real part is nothing else than a plane wave. So this is describing propagation. This is now a real exponential, and this is describing attenuation. So basically what you have is that if your medium is conductive, then as the wave propagates into this medium, it also dissipates its energy. So the wave becomes weaker and weaker, and this means, of course, that this energy goes into moving the charges of this medium, and so it goes into current and thermal dispersion. It is customary to quantify this, so the effective penetration of the wave into this medium, and of course this is an exponential, so it theoretically goes to infinite, but of course it practically doesn't. And it is customary to define the skin effect as 1 over this attenuation coefficient, and this says more or less that the wave cannot penetrate into this conductor more than this depth. And for a good conductor, so as long as this relation holds, then your skin depth can be written in this form. This is in meters, so it's a function of the conductivity, of course, because there has to be conductivity to trigger this effect, and also frequency. And this is very important because it means that in the same conductor, like X-band waves will not penetrate as deep as P-band waves. So X-band is 10 gigahertz, P-band is 300 or 400 megahertz. For radar, so for what we will see, let's say for radar looking at the Earth's surface, unless we consider the case of man-made objects, I will say that this is mostly the water contact. So, for example, if you look at the ice, then you can have a propagation for hundreds of meters or for a few meters, depending on the water content of the ice. So, for example, if the ice is melting, then most likely you have water at the surface, and this is going to act as a conductor, and this is going to block your signal at the surface. But if the ice is dry, then you will most likely penetrate for meters or tens of meters or even hundreds of meters. So, waves and targets. So maybe this is something that you do not know by heart, as in the case of the plane waves. So in this part of the course, we will consider the interaction of our waves with the target. And so basically, what is a target? A target is a region of space for which the characteristic parameters are not the same as in the other part of the space. So let's say a bubble of air is not a target, but you are target. So this is quite complex. This is quite complex because all we know so far about waves has been derived under the assumption of a homogeneous medium. So the characteristic parameters are constant. So how do we deal with this spatial variation? Well, let's say as a first approximation, which would hold when oops. Sorry. Sorry guys. Here we go. So, as the first approximation that more or less is valid as the frequency gets higher, you can assume that you end up with the old-fashioned Helmholtz equation with a slight modification. The wave number changes with the frequency. Changes over space. So it's k of r. This is not exactly true. If you want to see the real expression, I need several lines to write. But at high frequency, this is a sound approximation. So let's call this the space-varying Helmholtz equation. So how do we solve it? Now the general idea here is to decompose the field as the sum of two terms. So one is the incidence field. So this is the field that we have in space in the absence of our target. So this is just the field we are transmitting. And then you have the scattered field, which is the field that is just due to the target. So it is the field that it is the extra field that is generated by the presence of this target. So let's write k as, or rather k square as k0 square, which is given by the parameters in the region where the waves are propagating, let's say in air now. And now let's define this delta of r, which represents the spatial variation of this field. So if we write k squared in this way, then we can write Helmholtz equation like this. And so we end up with this new equation, which is very interesting because it says, you see, this is the space invariant Helmholtz equation. It doesn't equal to 0. It equals to a new term. And so this is equivalent to an extended source. So let's say that, at least as the first approximation, we can treat this space variant problem by transforming it into a field that is propagating in a homogeneous space, K0, with a source term, this one. So this plays the role of the extended source that was presented a few minutes ago. And this is a very powerful representation. Now, if you subtract the wave equation for the incidence field, I just remember you, is the field that you have in the absence of the target. So the Helmholtz equation for the incidence field has to be equal to 0. So if you subtract this one, then you end up with this equation for the scattered field. And so you have that the scattered field is given by the Helmholtz equation plus the source term. So let's say the combination of the spatial variation of k0 squared, this delta r, multiplied by the total field, this is the total field, is the source of your scattered field. And this is your entry point for the characterization of the scattered field. Now, okay, and this is what I've just said. So, since, no, one thing more. Since this is equivalent to an extended source, then you can apply the very same format and say that the expression of the scattered field is given by the integral of spherical waves modulated by this term. So now this is equivalent to your source, so you are emitting a spherical wave for each point in this source. Not bad, huh? This is not bad. This is a big step ahead. Now, let's see. Let's take this equation as it is. So, what does it mean in practice? Well, I want to analyze carefully. So, features or physical features of your target, your total field, distances, so geometry, and again distances, geometry. So in a radar remote sensing problem, this is the scattered field which is received by your radar. So this is your data. This is what you can measure. Huh? What you have to do, what you want to know as a scientist, or what you want to know because someone is paying you to know it, is how this object is made. So this is your unknown. And this is your total field. Now the total field is the sum of the incident field and the scattered field. So how do you compute it? This means that to compute the scattered field at the position of your radar, so to have a mathematical expression for your data, which is what you will need to do your inversion and to design your algorithm, you need to know the scattered field at the target. So, big problem. Big problem. So, how do we get away with that? Well, here we have to thank the famous physicist Bohr, the same as Dieter, and who proposed this approximation. Basically, the approximation is that the incident field at the target is much stronger than the scattered field from the target. So, as long as this is true, then you can substitute the total field for the incident field. And this one, you do know it, because you transmitted this field. So since you know the features of your antenna, since you know the position of your antenna, then you can compute the exact mathematical expression of your field everywhere. So now you have, this is our data. This is geometry, R minus R prime. This is geometry, so we can control it. This is our incidence field, we can control it, and this is our unknown. And based on this equation, we can start working with the radar imaging system. Okay? This equation is basically what we will assume throughout this course. Is it correct? No. We have spectacular drawbacks. In the first place, it will not account for wave extinction. For example, typically, as you are propagating through some medium, then you also have extinction, and this is not into the picture. And so you have to, let's say, this means that extinction will be lumped into these other terms. So what you can measure is no longer the physical structure of your object, but the combination between its physical structure and its extinction. And wave refraction is not in the picture either. You can bring it in the picture, but you have to take care. It is certainly not in the picture in this form. And also multiple scattering is not here. And so for multiple scattering, you can, for example, doing the same graph. Can you see here? Until here? Okay. So, multiple scattering. A very simple case of multiple scattering. This is your antenna. This is one target. This is another target. You have an incident field, scattered field from the first target, incident field, scattered field from the second target. And this is the situation that this approximation depicts. But we are totally missing the field from this target to this other target that goes back here and vice versa. And then you can assume as many interactions as you like. So We are not treating this. So, basically, how do we, again, why is radar remote sensing so popular, notwithstanding all of this limitation? Well, because in many cases, with a good physical modeling, we can interpret the result from this inversion and still end up with a sound, how to say, physical characterization of the target. And so this is more or less it concerning the introduction of this course. Now, so this is the second time we met. So at the end of the last lecture, I got that many of you are happy if we revise the fundamentals of antennas. Do you confirm it? Okay. Just as a curiosity, how many of you took the course on antennas? Everywhere. Okay. Where did you attend it? Okay. Okay. So it's 1, 2, or okay, what's 1, 2, 3, 4, 5. Okay, so I would say 60%. So I would present a few slides for the remaining 40%. For the rest of you, maybe it will be boring. Feel free to correct me if I am too rough for my interpretation. So in the first place, sorry, this is in Italian. I had no time for the translation. I use a lot of mathematics, so I think that mathematics is a universal language. So I guess that we will understand like 90%. But I commit to translate this and put it on the web folder. So sorry for that. So what is an antenna? An antenna is a transducer between the field and the signal, and it acts in two ways. So you get a signal and it produces a field, or you get a field and it outputs a signal. So concerning transmission, well, what to do is that you apply a signal and you get a field that will depend on a lot of things. It will depend on the geometry, so on the shape of your antenna. It will depend on the field itself, so also on the frequency. And let's say, and I apologize here for all the antenna guys here, this is a very rough treatment. So we will assume that simply the time variation, let's say we will assume that you have a distribution of sources along your antenna. So how to say that each point of your antenna is acting like a point source, and we will assume that the variation, so the temporal variation of your signal at each point on your antennas is proportional to the signal that you are using to feed your antenna. So this is not 100% true, but let's say that for this course it is a nice approximation. So basically the equation that we want to solve is the Helmholtz equation with an extended source term, this F, which represents the let's say the field inside of the antenna, which we further approximate as a time signal at every point on the antennas, or zero, just outside the antennas. So how do you compute the field from this antenna? Well, it's very easy. You just launch a spherical wave from each point of this antenna, and so this is the formal expression. If you do so if you approximate these terms here, so this r minus r prime, well, r prime is a point on the surface of this antenna, r is whatever point in space. So if you assume that your antenna is centered the origin of your coordinate system, and which makes sense if you are considering to calculate the field very far from this antenna. The farther you go, the smaller your antenna looks. So this approximation becomes more effective. And so you can model the field in this way. This is the Fourier transform of your time signal. So this is your information, if you like. This is the phase which is due to the distance. This is the intensity decay due to the distance. And here you have this term, which is basically the integral of a plane wave over your antennas. And this is nothing else than the Fourier transform of your antenna. So basically what you do is this Fourier transform, and you can also notice that this term is only depending on the direction. So the information about the distance from your antenna to a point in space is here. This is the information of your signal, and this is just a term that changes with the angles you are considering. Very simple example. I am considering a short antenna like a piece of wire. I do this calculation and I end up with this expression for the directivity. If you want to visualize this, I think that you saw something like this with Professor Monti. Did you? Okay, so I can catch you. So if you want to display this in space, this is a MATLAB code. Yeah? So this is your antenna, and the color. And the color is proportional to the intensity of your field. So if you have an antenna like this, then the maximum, so the peak of the power is along this band, let's say. And of course it is, you have no dependency on this direction, because your antenna is symmetric in this direction. You can do exactly, you can apply exactly the same argument if you have a planar antenna. So in this case, by emitting a plane wave from any point on your antenna, then you end up with a field distribution like this. So let's say that the field is mostly emitted in this direction, and of course the size of this lobe is proportional to the wavelength and to the inverse of the size of your planar antenna. So I think for the 60% I am going too slow, but what about the 40%? Is that okay? Okay, so this is it. Okay, this one I can skip it. So concerning your reception, so you want to use an antenna now not to transmit a field but to capture a field, and so and transduce it in the shape of a signal. So again, the exact calculation is not at all easy to do, and I don't want to do it. So I will just retain this approximation, this very rough approximation, and I will assume that the signal is just proportional to the integral of your incident field on your antenna. As simple as that. What you end up with is that also at reception you have a directivity term. So let's say that the amplitude of your signal is changing depending on the direction of your field. And magic, it is exactly the same as in transmission. This magic is called the reciprocity theorem, which again we will not treat here. No, I think that this is easy. So now some considerations about the power that is transported. Well, if you consider the case of a point-like antenna, then of course by symmetry, simply by consideration about symmetry, then you have a perfectly spherical wave, which means that the power is evenly radiated on all angles. So if you want to compute how much power does radiate through a small surface, dA, then all you have to do is to take the total power divided by the surface of this sphere, which is 4 pi times the square radius, and multiplied by this area. And this is defined as the spectral density. So it is the total power divided by the surface of this sphere. This is of course correct for a point-like antenna where all the power goes everywhere. Whereas for a real antenna, we saw that you have a directivity term, and indeed this power density is rather expressed in this form. It is again the total power radiated by this antenna divided by the surface of the sphere. So again, this depends on the distance. And then you have a factor G. This is always larger than 1, and this is called gain. And a directivity factor, this f of theta and psi, which is a positive function between 0 and 1, which basically is modulating this signal. So basically this term G is telling you the capability of your antenna to focus the field in a certain direction, whereas this other term is directivity. It's just telling you how the field decays if you move it from the peak direction. So if you put together this expression with the obvious condition that if you integrate all your power over the whole surface of the sphere, then you have to get the whole radiated power again, because power cannot disappear. Then you get this expression, which is very nice, and if you say a physical meaning, well, it adds a physical meaning to the gain. So the gain is the ratio between 4 pi and the integral of this directivity function. So basically, again, if your antenna has a very large gain, then its directivity function is will for sure exhibit a very narrow peak. And of course it also means that the size of this antenna will be bigger. So for a planar antenna it is very easy to show that the gain depends on the size on the area of your antenna according to this relation, and you can prove that this is a general relation. Of course, in the case of a real antenna, then you also had to account for a coefficient which traces the efficiency of this antenna. So let's say that the gain is multiplied by this term here, which is accounting for the eventual presence of thermal dissipation or a mismatch of the impedance of the front end, so that the power is bouncing back instead of being radiated. And you also define this effective area, which takes into account that the total power received by your antenna is, and so let's say the total power that is goes in the signal produced by your receiving antenna is not directly proportional to the area of the antenna, because you have losses, and again you can prove that the gain is always related to the effective area according to this relation. And I think this is more or less it. What is very important, so I know data baseline. What is very important for this course, for the development to come, is that this kind of exercise is very clear. So this is called the link budget. I think you all saw it more or less in some previous course. And let's say that you are putting some power here at this antenna, and then you are considering this particular direction, and you are receiving the field here with this other antenna, so with this direction with respect to the field. So you have the spectral, the power density at the receiver, which will be given by the total radiated power divided by the square of the distance, okay, 4 pi. So this is what you get from a point like antenna. Then you multiply this by your gain and by your directivity function. And this is the power density at this point. So how much power is captured by this other antenna? Well, you take the power density, multiply by the effective area of this antenna, and also by the directivity function of the receiving antenna, which is not 1 unless this is pointed exactly towards your receiving antenna. And so this is what you end up with. This is easy for everyone. Also, this kind of graphs, are you all familiar with this? So this is basically, those are graphs that are used to represent how the power is radiated in different direction. And so, for example, this is the power along elevation. So if you assume this antenna, then this is the variation in this plane. So let's say as a function of theta. And this is the elevation in the other plane. Of course, for a real antenna, you have different polarization. So if you want to characterize a real antenna, you have to do this for the vertical and the horizontal polarization separately. In this case, you see this is in dB, and so the gain of this antenna is 29 dB. And I would say that the effective lobe, when it goes down by 10 dB here, so the effective lobe of this antenna is 10 degrees, more or less. There is an alternative to this representation, which is given by this polar graph, where basically the radius of this line changes as a function of the angle, and it is intended that the radius is proportional to the directivity in that direction. So basically you see that this is the peak of directivity, and then you have almost a zero here, and then a side, and then of course also submission in the opposite direction. This is a pictorial representation of the Cosmos Skymet system. So with the solar panels and the SAR antenna. So this is the radar antennas. In this case, it's planar antennas made of TR modules. So you can compute the field according to what we have just saw. And if you want to see any information, there is everything on the website. And I'm really finished. So the Poynting vector, you can show, and I will not do it, you can show that the power density is given by the vector product between the electric and the magnetic field. So the absolute value, the magnitude of this power density is given, of course, since they are always perpendicular, is given by the product of the magnitude of E and H, and since these two are always connected according to the characteristics of your medium, then you can always write the power density as the square of the electric field divided by the impedance of your medium, which is always 377 ohm for the vacuum. And so what else? I think this is more or less it. If you want to put all the elements together, then this is the expression that you get from the field emitted by an antenna. So you have that this is the total radiated power. This is for pi. This is the spherical divergence, efficiency, gain, directivity. All these terms are under a square root because we are considering the field now. And this is your pulse in the time domain, and we with its delay. And of course, by comparing these two expressions, you can see that this directivity function is nothing else than, so it's proportional to the squared absolute value of this term that can be computed from the knowledge of the shape of your antenna. Okay, so for this part, this is more or less it. I hope it was not too boring for those of you who took this course. And now I would just like to apply this and do a couple of exercises that would be nice to see. So, disconnecting this one. So everything was clear. Was a bit boring, maybe. So, I want to consider this problem. So I have a source here, point-like source, and here I have an interface between two materials. So let's say we have here a propagation velocity v1 and v2. This has a finite length L. And I want to compute, sorry, you have an incident field here. Let's say that this position, we call it Rm. I want to compute the field, the generic position R here. And then afterwards at the generic position R here. So in the other half space. And so for sake of simplicity, let's say that this point is the origin of our axis, so it's 0, 0, 0. The coordinates here are 0, 0, 0. Of course, this is a well-known problem, thing that you solved in physics courses. So we will then end up with the Snell law, but it was demonstrated in a very different way. You know, in physics or electromagnetic courses, you calculate the field here according to some boundary conditions, and you use this to compute the complex amplitude of the field, of the plane wave that form the field in the different directions. Now, I want to do it plane just with spherical waves. We will add something, which is the possibility to account for a finite length of this interface. So we will lose something, but we also win something. We get the size of this interface in the picture. So now let's do the things very carefully. We have this incident field. So let's assume that this field is propagating from this point. So you can write it like everywhere in space, like 1 r minus rm. Those are vectors. And okay. If I assume a monochromatic wave, this is it. Otherwise, I can multiply this by S of f, which is the Fourier transform of my signal. But it is not necessary here, so just ignore it. We assume a plane wave. So how do we compute the field everywhere? Well, according to what we have just saw about how to treat the target, what we will do is we notice that here we have a change in k squared, or a change in the velocity. So it means that our field will be generated by, let's say that each point for which the velocity is different than the velocity of the first medium will act as a new source of spherical waves. With attention, we are assuming that the propagation velocity is constant here. It changes all of a sudden at this interface, and then it is again constant here. So I do not have to consider a point, so let's say a spherical wave for any of these points inside this new medium, because there is no change here. So the one change occurs at this interface. So if I want to compute the field everywhere, I just have to compute I just have to consider new sources of spherical waves where I have a change of propagation velocity, which means here. So your field in this space, let's call it E1. Will just be given by the integral over this interface of what? According to the approximation we did of the incident field at this surface times a spherical wave from each point on this surface. So let's say one. Let's call this. Where I am using R prime as a generic point to indicate the coordinate of a generic point of this surface interface. Okay, this is exactly what we saw in the first part of this lecture. Now let's try to simplify this expression, and of course the first thing to simplify is to notice that this R minus Rm, which is the distance from which is the distance from let's say any point on the surface. I call it R prime. So R prime minus Rm. This is the distance from each point on the surface to the source. So distance means this one, and you can approximate it around, for example, the center of this interface. So we say that this O is the origin, so this one is 0, 0, 0. I can simply take the Taylor expansion of this square root about 0. What you end up with is R of m, not the vector, the distance, so this distance. Minus, take care about the sign, xm Rm. This is it. Now, let's say that I am just interested here in this plane. So let's put some coordinate. This is y, this is z, and so x is the coordinate orthogonal to the blackboard. I want to stay in this plane, so let's say that xm is 0. And what you get is that this is equal to R of m. So this term goes away because I just want to stay in this plane. So this term tells you the variation with respect to y prime. So if you increment y prime, the distance is increased, right? And so it means that you have that the final sign has to be positive, and indeed the ym coordinate here should be negative, and so at the end you have the positive sign. let's call this angle theta I incident, and what you get is sine of theta I times y prime, and then this is zeta m divided by the distance, and so if this is a sine, this is a cosine, and here we go. I just want you to notice this. So if y prime is increased, we are moving away from the source. So the distance increases. So you see there the expression of the distance increases with y prime increasing. If you increase z prime, then you are moving closer to the source. And so you have a sign minus. So just take care about the signs here, because if you miss the signs, then you screw it up. So this term here, at this point, this term here, you can substitute it by assuming this expression. Here's this. Now, what I should do here is to take this expansion and plug it in here, right? In truth, what you want to do is to approximate the amplitude in a very rough way, so like at order 0. So for this term here, I will just assume R of m is the distance to the center of this interface. Whereas for the phase, I will retain all of these terms. And now I ask you, why do I do that? So, just to be clear, I will approximate this incident field like this. Why did I do that? Why am I considering different approximations in different parts of the same formula?
Because the amplitude is so.
You make a small error, while in the phase you can make it's a big
It's the
mistake.
same. Actually, it's the same. It's one is too slow. It has no charger, and the other one is more. It's faster. The phase is way faster than the envelope.
Yes. Well, I would say that phase, you always read it modulus 2 pi. So if you change it, if this term gives you a variation of 2 pi or pi, let's say, which can take a very short distance. So like typically, if you move by half the wavelength, then you have a phase variation that can be on the order of pi, and this changes your phases completely. For the amplitude, if this is 1 kilometer or 1 kilometer plus 1 meter, it doesn't change. So this is the expression of the field, of the incident field. At this point, I will do exactly the same approximation for the scatter field. So for each wave emitted from each let's see, so I have scatter field R. This is equal. I can let's say that this is proportional to, I am just skipping the constant terms like this one and this one. This term I am not considering it because we say that we just compute the field at this interface where z prime is 0. So there is no need for a 2D integral. I just need a 1D integral. And then of course here I have a spherical wave from R prime to this point R. And so again here I should write this one. So retaining exactly the same approximation and defining this angle as theta of s, then I can approximate this distance as so I'm not doing the calculations again. Oh, yeah. I'm not doing the calculations again, so this becomes so it's always a sine and the cosine, but you want to check that the sine is correct. So if this is y prime, sorry, yeah? Prime. So if y prime is increasing, then you're getting closer to this point. So your distance decreases. And indeed you have a minus. If z prime is increasing, then you go closer, and so this one, it has to be a minus. Okay, so if I plug this approximation in here, what I finally get, and I write here, so scatter field in the first half space of let's say, from this medium. This is proportional to the integral of the incident field, so it was minus j 2 pi v1. We say z minus sin theta s 1 prime right. Right. And so the z prime of the z prime sorry, z prime is 0, sorry. No need for z prime. There we go. So now it is here that the length of the surface comes into the picture. Yeah.
Why there isn't the minus sign before the sign of theta h?
Are you happier this way? It's minus minus is plus. Okay, so I just forgot to. But what is important is that those two signs are different. Right? Because you have increasing distances here and decreasing distances there. So it is now that the length of this interface gets into the picture. So what we are losing as compared to a rigorous magnetic modeling is amplitude. We are just writing here proportional to. So we are not able, using this modeling, to compute the complex amplitude of the field. But we are able to bring this length in the picture, because this integral can only go from minus L over 2 to plus L over 2. And this integral is easy. You will find with this integral. This is a linear term. You see, you can write this this way. So you are integrating a phase function with some slope over an interval from minus L over 2 to plus L over 2. The result is zero. You want me to do that? step by step. It's easy, yeah? It's easy. Guys. Do you agree? Okay, it's exactly the same. So the alpha here is all this term. This is your alpha. So you get j2 pi f. Okay, let's say f over v. Okay, well, we can let it this way times the difference of the signs. Right? And here you have there you go. This is the difference between two complex exponential with the same phase, just the sign changes. So this is a sign. So the upper term is equal to 2j times the sine of sorry. Okay, we're optimistic. So this is 2j times the sine of there you go. There you go. What does it tell us in space?
C.
This is a C.
Right.
Sure. But what does it tell us? What does it tell us? So if you do so, you see, this is a cardinal sign, and the argument is given by the frequency, velocity. So this is the wavelength is in the picture. Then you have the difference between the signs of the two angles and the length of this interface. So you can simply, I am canceling this out, okay? So if you draw a graph of this function, I can do this in, for example, I take as variable this difference. So I put here sine of theta I minus sine of theta s. When it is 0, I have the top amplitude. Then it decays, like a cardinal sign. And you see that the first 0 is in lambda divided by L. So basically, the width of this loop is lambda over L. So if you want to represent this in this context, this means that your field is mostly emitted in this direction, and the width of this loop changes according to the wavelength, okay, to the ratio between the wavelength and the length of this interface. So if you have a very short interface, then this becomes huge. And you are getting close to the case of a point source where you have emission everywhere in space. As this one gets larger, this loop gets very narrow. And when it gets infinite, or rather, when it is much, much longer than the wavelength, then you can assume that you only have emission in this direction. And this is exactly what you know from physics. Specular reflection. And so basically, you can tell that you have this perfect reflection, like a ball in a pool, no? Tuck, tuck, only when this surface is much larger than your wavelength. Otherwise, the power is spread according to this law. So the shorter your interface, or the bigger your wavelength, and the more spread your power is. Okay, sorry, just to give me a feedback to adjust the next lectures. Who found this new? Okay, newish. Okay, who found these absolutely well known and already seen? Don't be shy. So you're all happy to see things like that. Okay. Okay, this is important. Okay, so we eat on Monday. On Monday we go in this other space, and we will start talking about radars, real radars.